Hello, everyone. If you can hear me, please use the Q&A to let me know. Okay, thanks. Okay, so good afternoon, everyone. Few announcements before I get started. First of all, hopefully you've got my email with regard to the extension on the quiz and lab 2. So the new deadline for the quiz will hopefully be released today, sometime after the class, and the deadline will be the Monday after the reading week. And for lab 2, the deadline will be on Wednesday. As I mentioned in my email, please do your best to finish it this week. Lab 3 has its own workload, and because we really cannot extend lab 3's deadline as well. It's a continuation every 2 weeks. So since that one is not going to change, you will be overwhelmed if you don't finish it on time. And then we actually gave those groups who finish by the original deadline some bonus points. Lab 1 also has been graded. We're in the final steps to finalize the grades. They will be released soon, within few days. So that's that. Yeah. So those are the announcements I had for today. So let me just get started with the lecture. Okay, so we're talking about scheduling uniprocessors. The first scheduling policy. Oh, before I go, let me give you full screen. Okay, so the first policy we're considering is first come, first serve. It's very easy. Basically, we have a FIFO as our ready list. I got a question just to confirm, is lab 2 due this Wednesday or Friday? Oh, none. So publish. The original deadline for lab 2 was this Friday. Those groups who finish and submit by Friday before 8:30, they will get 5% extra points. If not, the extended deadline is Wednesday after the reading week. I believe it's October 21st or 20th. I'm not quite sure. So, okay, look at the email I sent on Piazza. Okay, so first come, first serve is very easy. Basically, you just have a ready list that implements FIFO. Every time you get CPU, you run your CPU burst until you finish that CPU burst. Now, at this point, you probably want to go for I/O or whatever. So you're out. You go for I/O, and then you come back to the back of the list. Now, one thing to note here is that we're not talking about preemption at this point. So when a a thread, a task, a process gets CPU, it just executes as much as it wants until it yields the CPU. We got a question, is the bonus applied to lab 2 or the labs in general? No, so there are 2 bonuses so far that I've announced. The bonus that I just talked about only applies to lab 2. So if you finish by lab 2's original deadline, you get a 5% bonus. There's another bonus that we give if you don't, like from for lab 2, lab 3, lab 4, and lab 5, if you don't use any grace days, then you get extra 5% on your total lab point. Hopefully that clears it up. Okay, so here's an example. Suppose that we have 3 threads, and each one of them has what you can see over there as its CPU burst. For FIFO, we are interested in the order of tasks, arrival of tasks. Now, let's assume that tasks arrive in this order. First T1 comes, then T2, and then T3. And this is a diagram showing how tasks would run. So here on the x-axis I have time, y-axis doesn't really matter. So it's kind of like one-dimensional. So T1 is the first one, runs for its duration, for its CPU burst, then T2, then T3. So now we can actually do some calculations on this. If I ask you what is the wait time for T1, the answer is 0, because T1 did not wait at all. The moment it came, it just got scheduled at time 0. Assuming that all tasks were available at time 0, then T2's wait time is 24. Because it waited 24 seconds or whatever unit of time we have to start executing. And wait time for T3 is 27. Now, what is average wait time? We just add them up and divide by 3. That is our average wait time. Now, one thing to note, let me go forward and then I'll talk about more complicated scenarios. So now, what is the average response time? Now, if you go back to the definition of response time is the time from which a task arrives until it is completed. So T1, assuming that all of them were in the system at time 0, so from T0, from 0 to 24, that's how long it took for T1 to get processed. So that's T1's response time. T2's response time is 27. T3's response time is 30. So we add them up, we divide by 3, we get average response time. So I got a question that is asking, is there a possibility that T1 does not run to completion and other threads will never be executed? With FIFO, when you get the processor with this simple one that we have talked about, you get to keep it as long as you want. So if T1 is just a while loop, an empty while loop, then we're screwed. So T1 will execute forever, if that's what you were asking. Usually, in the examples that you will see, we'll give you CPU burst time, and that basically means how long T1 will execute. Now, let me talk about a little bit more involved scenarios that you might see in quizzes. So instead of like a simple T1 is 24, T2 is this, and T3 is this, you might get something that is more like an iterative task. You might get something like, we'll see examples of this, but just here at the beginning, I want to mention it. You might get like something like T1 does 24 seconds of 24 units of time of computation, and then it does 3 units of time IO. And then this is an iterative process. Then again, 24 units of time CPU burst, and then 3 times units IO. In those cases, again, what matters to us for wait time is when T1 comes to the ready queue for its CPU burst until it gets executed. And again, for the same thing, for response time, from when T1 comes back, if it is like it goes for IO and then comes back, from when it comes back until it leaves for that iteration. So you might get many of these, and then you divide not only by the number of tasks, let's say we have 3 tasks, but also you have to consider how many times T1 showed up. So you have to divide by that as well to get an average. Okay, so I got another question. Why is response time accumulative? I would have thought it would be 2433. Yes, so that's the definition of it. The definition is response time is from when you come to the system until you are done and you go out. So what you had there was just execution time. Execution time is 2433, but then the response time is, let's say you click a button, from when you click that button until you see that that letter show up on the shows up on the screen, that's your response time. Okay. Now let's say threads arrive in a different order, T2, T3, and then T1. Then this would be the schedule, and we will get totally different numbers here. So now average wait time is 3 compared to 17 that was before, and average response time is 13 compared to 27 before. This is very important. So just because the schedule changed, wait time and response times changed. If I ask you what is the throughput of this system, in both cases, the throughput is 3 tasks per 30 units of time. So the throughput hasn't changed. But as you can see, response time has changed just by reordering these tasks. So if we want to talk about the pros and cons of FCFS, the positive point about it is that it's simple, and the negative point about it is that short tasks could get stuck behind long ones. So average waiting time and average response time could hurt if you have a long task. So if you go back to the previous schedule, T1 was first, and T1 is a big one. And because response time is cumulative, we basically added the execution time of T1 to T2 and T3's response times. And that made average response time really bad. So by just reordering the tasks so that the small tasks run first, we got a better response time. This has a name, Convoy Effect. Let me do one of those on-air corrections here. So let's say that you were running one task and then 2 tasks arrived. So in this diagram that I have, on x-axis I have time, And then on top of this line, you can see the tasks that are scheduled by their colors. And here at the bottom of this, you can see the queue of tasks. So because we were running this task and 2 tasks arrived, they just get queued. Now, when the first task is done, then we run the blue task, and then we run the green task. Let's say another task comes. And let's say that this task was a big task. As a result of that, we might actually get a lot of tasks queued, because this one was a long one, and we were busy running this task. So every other task gets basically queued. I've got a question. Why would we need to divide by number of times the tasks? The task was split into if FIFO allows one program to run until completion, including I/O activity. I never said FIFO allows you to complete until I/O activity. So when you have an I/O request, you actually get out of CPU. You're no longer running. You are waiting. So you go, your PCB, your TCB will move to some waiting queue somewhere else. So you're out, and then you come back again. So FIFO allows you to have the CPU as long as you have work to do, CPU cycles. So if you call on a blocking I/O operation and you're blocked on I/O, then you're out. So you go out, you're now waiting for that I/O. FIFO allows other tasks to run. That's why we might want to divide by the number of times a task would show up. That makes sense. So if you only show up once and you have the CPU until you finish and you're done, then we don't divide because there is only one. Okay, I hope that clears it up. It was an important question. Okay. The next scheduling policy that we look at is round robin. And it's here to sort of mitigate the problems that we had with FCFS. We don't want the schedule to depend much on the submission order. And we really didn't like the fact that tasks would get accumulated in the ready queue if you have really a long task. So what round robin does is that it divides CPU time into time quanta that could be any number, any units of time, each time quantum, usually let's say something between 10 milliseconds to 100 milliseconds. And then a task would get CPU time until either it is done or until the time expires. And if any of these two happen, if the task is done, then it's done, it goes away. I'm sorry. If it's not, and it still has work to do, if it still has CPU cycles and CPU bursts, then the task would go to the back of the queue. So if we have n threads in our ready queue, and the time quantum is, the length of time quantum is q, then each thread gets 1/nth of CPU time in chunks of at most q time units. And it's important here, it's at most, because you could yield the CPU, for instance, or you could be blocked on I/O. And if that happens, then your time quantum expires. So as a result of this, no thread waits more than n-1 times q time units to get the CPU for the first time. So this reduces the bound on maximum wait time. With FIFO and FCFS, we really didn't have any bound because it would just depend on how long the task in front of you is. But here, no matter how big or how large or how long the task in front of you is, that task is going to only get the CPU for queue time units, and then it's going to go back to the queue, and then you're going to get it. So there is a bound on your maximum wait time. Let's look at an example. Let's say these are the numbers for your tasks or threads or whatever you want to call them. Here is how it works. So I have the schedule. Let's say the time unit is, the time quantum is 20. Then T1 gets it for 20 from 0 to 20. Then T2 comes. T2 doesn't need it for 20. The burst time of T2 is only 8. Sorry, I should have probably made these boxes proportional to those times, but my mistake. So anyways, so T2 only runs for 8 time units and it's done. It goes out. Then T3 runs for 20 seconds or 20 time units, T4, and now we're back to T1. After T1, we go back to T3, T4, T1, T3, T3. And then these are the numbers. So what is the wait time? Now it's important how we calculate wait time for each one of these tasks, right? So the wait time basically is the time that you spend waiting for CPU. That's the definition of wait time. So if you look at T1 and see which time durations T1 was waiting, you can see that T1 was waiting from 20 to 68 here. T1 was waiting. So before this, there is no waiting time for T1. T1 just gets it scheduled. Now T1 is waiting here to get it scheduled again. And then here to get scheduled for the third time. So we have 68 minus 20, this duration, and 120 minus 88, this duration for T1. Let's say, just to make this a little bit complicated, let's say after this T1 goes for IO and then comes back at 153. We're not going to count from here 125 to 153 as T1's waiting time, because at this duration, when it was done and it was doing IO, it was not waiting in this queue. So then it comes here. Now we start counting. If it waits in the queue for it to be scheduled, then that would be considered as its waiting time. Okay. Now, average wait time, well, you just add these numbers and divide them by 4. If you have iterative ways of tasks doing IO and then coming back, you first need to calculate one average for each one of those tasks. So each one of those tasks would get their own wait time. Then you take an average over instances that task showed up. And then here you get another average over tasks. So you would get 2 averages. I got a question. So since T2 is done in 8, does the remaining 12 time units allocated to another thread? Yes, that's a good point. Yes. So once one goes out, let's say T2 here goes out, we immediately schedule another one. We don't waste the remaining 12 time units not doing anything. We just allocate it to another task, which is what happened. So as you can see, T3 got scheduled at 28. And then you have average response time. So what is average response time? This one is quite easy to calculate. All you need to have for each one of these is to just look at the last time a task executed. So T1 finished here. So the response time of T1 is 125. T2 finished here. So the response time of T2 is 28. T3 finished here at the end. So the response time of T3 is 153. And T4 finished here. So response time of T4 is 112. And since we want average response time, we just divide by 4 and we get the number that we are looking for. Okay, let's have some discussions about round robin. The positive point about it is that it actually is better for short tasks. They don't need to wait for long ones. But bad thing about it is that it incurs a lot of context switching time. At this point in the lecture and going forward, whenever we discuss the different scheduling policies, we usually assume that context switching time is 0. As you saw here, we didn't count any extra time unit here between T1 and T2 when they switched. But in reality, actually, you're wasting some time here, right? So if you actually implement round robin, because you're making scheduling decisions every time quantum, you incur quite a lot of overhead for context switching. Now let's think a little bit about round robin. How does performance change with the duration of time quantum? What happens if time quantum is so long, is really, really long? What does round robin do? So the answer is, well, response time will suffer for short tasks because now they have to wait for longer periods of time. Now, what if it's too short? What if the time quantum is really, really short? What happens? So in that case, throughput suffers because we're going to context switch a lot. And context switching adds overhead. Overhead is bad for throughput. In the extreme case where time quantum is infinity, then what does round robin turn to? If you think about this question, you'll see that round robin actually turns to FCFS in that extreme case. Because what it basically means now is that when you get CPU, you run until you are done with your CPU burst. Okay. So setting this time quantum actually is something that those who implement these schedulers spend some time to figure it out. Let's see how it affects response time and waiting time in the next slide. Got a question. Why does wait time not suffer when the time quantum is too long? Oh, it does. It does. So wait time and response time are very, very related. So when you have more wait time, you definitely have more response time. So longer waiting times mean longer response times. So when I say response time suffers, basically what I mean is wait time suffers. Because in essence, response time equals wait time plus execution time. So if the execution time is fixed, then response time is directly connected to or related to wait time. Okay, so here's the question. Let's assume that there is no context switching overhead. I got another question. Is there a quiz this week, yes. It will be released hopefully today, but the deadline is not this Friday. The deadline is the Monday after reading week, so October 19th. Do you guys read your emails? I sent an email on this. Okay. Okay, so assume that there is no context switching. What happens when you decrease the quantum, the time quantum? Does the average response time always decrease? Does it stay the same? Or does it increase? So which one of these answers do you think is correct? I'm going to give you some time to think about it. Okay. The answer is actually all of them. So all of them could potentially happen. So the quiz covers the material only up to this lecture. Yes. So the quiz that will be released today will cover everything up to this lecture. Okay, so the answer basically is all three could happen. Let's see how. So this is an example where response time is going to decrease. Let's look at it. Let's say we have two tasks, one with burst time 10, one with burst time 1. If time quantum is 10, this is going to be the schedule, assuming that T1 is in front of T2. So basically what this is that T1 is going to finish and then T2 will run, and the average response time is 10.5. Now let's decrease Q to 5. Then this is going to be the schedule, and as you can see, the average response time went down. Now let's see a case where response time actually doesn't change. Here is the example. T1 and T2 are equal. And let's say the time quantum is 10. Well, because they don't really need that time quantum, the average response time is basically 1.5. The same if the time quantum is 1. So if you decrease time quantum to 1, the schedule is not going to change, and you get the same average response time. Now, third case where we're going to see an instance where the response time is going to increase by decreasing time quantum, and this is the case. Let's say the first one, time quantum is 1. This is going to be the schedule. T1 runs and then T2 runs, as we saw, and the average response time is 1.5. Now let's say we decrease Q to half. So here's what's going to happen. Now, what is the average response time this time? Well, you look at when each one of them finished. So T1 finished at 1.5 here, and T2 finished at 2. So average response time is 1.75, which is more than 1.5. So in the previous 3 slides, I showed you 3 different scenarios where decreasing the time quantum led to different outcomes with regard to average response time. So basically, it's very unpredictable what happens, and it would depend on the workload that you're running, the combination of tasks that you're running, and their characteristics. That's the gist of this question and these slides. Okay, let's continue discussing this. What should be the actual choice for time quantum? It really, as we saw, it's something that should be engineered. Should in some cases, and we'll talk about advanced schedulers in Linux. Usually, they all have time quantum, but this time quantum changes dynamically by the workload. We'll see more about this. Yeah, so initially when you had Unix systems with few users, 1 or 2 users, you had to have a certain time quantum. As you started having more, then what should this time quantum be? I got a question. So the use of the word always implies that it's true for all potential tasks. So it's the real answer just so isn't, oh, my fault. I actually didn't pay attention to those 3 answers. Let me see. Oh yeah, you're right. So I take it back. I didn't read the questions well. So 1 and 2 are not correct. They say always decreases or always increases. They're false. Could increase, decrease, or stay the same. Thank you for mentioning it. Okay. So basically, answer 3 was the option 3 was the right answer. Okay. Okay. So typically in systems, as I mentioned, time quantum is something between 10 milliseconds to 100 milliseconds, and then the time it takes for context switching is something between 0.1 millisecond to 1 millisecond. These numbers, again, these are just estimates for typical systems. It really depends on the system, the workloads, and how things are implemented. The one important thing is you always want the context switching overhead to be roughly about 1% of the time quantum. So if you have, one of the most important things for you when you're setting your time quantum is to measure how much overhead you have for context switching, because you want this overhead to be negligible compared to your time quantum. Otherwise, you will spend a lot of time bringing a task to run, and then you're going to just interrupt it right away. If, let's say, the context switching is half a unit of time, and then time quantum is also half a unit of time, then you have basically 100% overhead, and that doesn't make any sense. Okay, let's compare FCFS and round robin. So assuming that there is no context switching, then is FCFS, is round robin always better than FCFS? Well, it depends, right? It really depends, as we've seen in the previous slides. It really depends on the workloads. Let's look at an example. Let's say, suppose that we have 10 tasks. Each one of them need 100 seconds of CPU time. Basically, their CPU burst time is 100 seconds. And let's say the round robin quantum is 1 second. So here is how FCFS does this, assuming that tasks are ordered by their numbers. Because all of them are equal in their sizes, each one of them is going to run for 100 seconds, and T10 is going to be done at 1,000. So this is going to be the response times for all the tasks under FCFS. just note that I'm using completion time as well here, which basically, if your task comes and goes once, then completion time is basically your response time. If you have an iterative task, then completion time doesn't really have any meanings because your task is just keep repeating. But if your task comes and goes and that's it, then you have a completion time. Now this is what happens with round robin. So in order for you to see what the response times are, you just look at the last instance of each task, see when they finished. So T1 finishes here, 991, and then the last one finishes at 1000. So these are the response times under RR. So as you can definitely see, all these numbers are higher than FCFS's numbers. So in this case, round robin is giving you worse response time than FCFS. Okay. So it really depends. This bullet point is saying that if when you have all your threads having the same length, then FCFS is better than round robin when it comes to response time. The other thing that you need to pay attention to if you want to implement round robin is that it's not just the overhead of context switching per se, you know, all the things that you do in kernel to make a task ready to execute, and then you give it you set PC and then the task starts to execute. So that takes time from when you preempt one task and then start another task. That's one overhead of context switching. The other important overhead of context switching is basically cache reuse. We talked about this previously. Let's say you have been running on a CPU. As a result of a task running on CPU, its data usually resides in the caches. So as a task executes, loads, and stores, the processor, the hardware automatically caches the data in its caches. And when you context switch to a different thread, now this new thread starts caching its own data, but then you have to consider that the cache has limited capacity, and bringing new data means evicting old data. So when you come back, you context switch back to run, now your data is no longer in the cache. So if you have really short time quantum, then what will happen is that, first of all, you're going to context switch a lot. And then the second is that basically nobody is going to use caches, because every time they fill the cache and they're ready to see the benefit of filling the cache, you're going to evict them and put a new thread to run. So if anything, it's going to introduce, in some cases, more overhead caching. If you're spending time to cache, it's better in those scenarios not to cache at all, because you're not going to use it anyways. Okay, so let's continue with our comparisons of FCFS and round robin. This is, I believe, an example we saw earlier with FCFS. So we had 3 tasks. One was executing for 8 time units, one for 24, one for 53, and one for 68. The best schedule under FCFS in terms of response time is when the shortest task runs first, and then the next shortest task, and then the next one, and the next one. So this schedule, you can convince yourself that gives you the best response time. any other ordering of T1, T2, and T3 will give you a higher average response time. I got a question. So based on the unpredictable nature of response time, is the time quantum calculated based on trial and error? Hold on to that question. If you don't get an answer by this or next lecture, ask it again. We'll talk about how in modern systems this time quantum is set. And yes, it sort of does. Not really try and error, but you can basically look at the characteristics of your applications and try to set that time. Okay, so in this table, the first, so I have wait time and then I have response time. Again, very related. Now, the first row of each one of them is the best FCFS scenario and the worst FCFS scenario, the last row. And then in between, I have different time quanta. So we're going to see these numbers. So wait time for T1 under each one of these. So basically, we have 1, 2, 3, 4, 5, 6, 7 different schedules to consider. And for each one of them, we're going to look at T1, T2, T3, T4, sorry, T5. Oh, this guy should be T4. Another on error. Not even sure if I can do it on there. Yeah. Okay, sorry about that. Let's see. So this was this is the best FCFS, and these are the numbers for this best FCFS. So if you look at T1, the wait time for T1 is 32. So that's how long it took for T1 to get scheduled. And the response time is 85, which is basically when it finished. And so on and so forth. So I'm not going to go through them. Now, what is the worst FCFS? The worst FCFS is when the order is basically in the other direction, when you have the longest task running first and then so on and so forth. So in this case, you can see these are the numbers. Now, do this for yourself. Every time I do these updates, my computer runs very slowly for some reason. So this is, for instance, for the case where the time quantum is 8. So this is the order, so on and so forth. I'm not going to spend time doing these numbers. So these are the numbers. Now, let's look at these numbers and do some observations. In particular, let's look at T2. So if you remember, T2 is the shortest task in this workload. Look at the wait times and look at the response times. As you can see, there is huge difference from 0 wait time to 145, and then all the numbers in between. The same with response time. There is a huge range for T2, sorry, which was the shortest. Now, what was the longest task in this workload? It was T3. Now look at T3 numbers. Other than this this worst case, which is 0, and here, which is 68, all the other numbers are the same, basically. So this should tell you something about how variation in time quantum can affect different tasks. If you are a really long task, you care less about time quantum. But if you are a short, really short task, then the use the choose of how you choose time quantum really affects you. So this example should make that clear. Now, what time is it? I guess we have time to have a break. So let's have a break for 2 minutes. Get up, stretch, do something, and then come back in 2 minutes, and we'll continue. Okay, we're back. So this is the third scheduling policy we're going to talk about. Shortest task first, SGF. And the idea is, can we always mirror the best FCFS scenario? If we really care about average response time, can we do that? So the idea is, let's run the shortest task in the queue every time. And another name for SGF is shortest time to completion first. So whichever task that I have that has the least amount of CPU time to finish, I'm going to run that one. And then you might actually think about a preemptive version of this, where let's say you start a task that had the least amount of work to do, and then another task came to the system that had even shorter CPU burst. If that happens, then you preempt the current task and you start running the newcomer. And this could be applied to the whole program, say considering the I/O times, but usually what we ask in the exam is basically it's with regard to your current CPU burst. So we don't really care about the future CPU bursts and I/Os. Every time a task comes, let's say if it is an iterative task, which does CPU, then IO, then CPU. So every time it comes, we just look at this instance of the task and see how much CPU burst it has. And based on that, we schedule. Again, as I mentioned, you could potentially look at the entire program, considering the IO bursts and future CPU bursts. But if not explicitly mentioned in the questions, you should just look at that particular CPU burst. How does the processor know which task has the least amount of work to do? Exactly, that's a $1 million question, and that's correct. That's why SGF is not practical. It's impractical to implement. We're just talking about it because it's an optimal schedule. So we're going to use SGF as a benchmark to compare other scheduling policies against. But as you've mentioned, in reality, you cannot implement this because you don't know how long each task takes, usually. In some certain cases, you know, let's say if you have a real-time system and you exactly measured the execution time of your task, and there is like you're gonna disable all the interrupts and exceptions and all of that, and you basically know exactly how long it takes, then you might be able to implement SGF, but usually that's not the case. So SGF is optimal. It basically minimizes average response time. Got another question. Can't you just count the number of CPU instructions? I actually very much appreciate this question. So somebody is asking, to know the execution time of your task, you just count how many instructions it has. But is that a really good measure of execution time? Not really. So you have different kinds of instructions. So a multiplication instruction takes some amount of time to complete. If it's done on floating point, or if it is done on a double, the same with load and store. They would take different amounts of time, whether or not your data is cached, for instance. So different instructions take different amount of time, and that is really not deterministic. So the other thing is you sort of don't really know how many instructions you're going to run, right? If you have branches in your code, that would depend on a dynamically given input data, then you might actually in your code have a long loop, but because the condition of that loop doesn't hold, then you would never dynamically execute that code. So it's hard to say if the code that I'm seeing is going to be executed, or which parts of the code is going to be executed when you start running. So these are all unknowns until you start running your program. Hopefully that answered the question. Okay. So here's the proof of why SGF is optimal. And the idea is that you can say, okay, let's assume that it's not optimal. So there is another schedule that has an average response time that is better than SGF. Then you can look at that other schedule, which shouldn't be SGF. So what that means is that if that schedule with minimum average response time is not SGF, then at some point you have scheduled a task that is longer than some other task in your queue. Because if all the tasks that are scheduled are ordered based on their execution times, then you have SGF. So if you're not SGF and you're still optimal, so there is one instance at least where you have scheduled a longer task instead of a shorter task. So now just swap these two tasks. So have a different schedule. So have another schedule that schedules the shorter task, doesn't touch any other orders, just changes these two tasks. Instead of running the longer first, it runs shorter task first. And you can actually show by this swap, you're going to decrease the average response time, which would in effect be considered as a counter, a contradiction to your first assumption that this schedule is indeed minimum and it's not SGF. So this is another interesting point with SGF. So it's optimal and we can prove it that it's optimal. So it's the best you can do, provably optimal, and the bad thing about it, though, is, before going to the cons of SGF, let's compare SRTF, basically the preemptive version of SGF, and FCFS. So if all tasks have the same length, then both of them are the same. So FCFS equals SRTF. Because when the length of all tasks are the same, then the order doesn't really matter. So FCFS does as good as SRTF. What if tasks have varying lengths? Then, unlike FCFS, SRTF schedules short tasks first. So those short tasks don't get stuck behind long ones. So this is probably one example, if not the only example I have with iterative jobs. So let's say you have 3 tasks, A, B, and C. And let's say A and B have very long CPU burst, as you can see. So they don't have any I/O. It's just a very, very long computation. Let's say C, on the other hand, has an iterative process. So it does 1 millisecond of computation, and then it needs 9 milliseconds of I/O burst. So it does I/O, and then it comes back. Let's see how different schedules schedule these tasks. Sorry, before that, if A and B get to run by themselves, each one of them is going to utilize the CPU 100% because they're going to run for weeks, let's say, for each one of them for a week. So they're going to utilize CPU 100%, and they're not going to utilize I/O at all because they don't have any I/O. On the other hand, if C runs, C is going to utilize CPU only 10%, but it's going to utilize I/O for 90%. Now, let's see what happens under FCFS scheduling policy. So once A and B get to run, the C is not going to see the light of the day for 2 weeks. So basically very, very poor average response time because C's response time is going to be really high. Now, what about round robin or shortest remaining task first? So It's easier actually to see them in a diagram. So let's look at them in a diagram. So I have both CPU and I/O. Now with round robin, one thing that you should know by now is that it really depends on the time quantum, how tasks are scheduled. Let's assume that the time quantum is 40 milliseconds, and let's see what happens. And let's assume that the order is basically C first, then A, then B. So in that case, C first executes, so C executes only for 1 millisecond because that was its CPU burst. And immediately afterwards, C starts doing I/O. While C is doing I/O, A is gonna run, and then B is gonna run. So C is back here. After I/O is done, C is back in the list. So C will be scheduled, then A, then B, and this will repeat. Okay. So if you look on average, the I/O utilization is about 11%. And CPU utilization is actually 100%. Now, let's look at round robin with 1 millisecond time quantum. So C is gonna again run, then it's gonna go and do I/O. While it's doing I/O, A and B are going to context switch back and forth. And then eventually when C is ready, C will be scheduled, and this will continue. So in this case, I/O utilization is much higher, 82%. And CPU utilization in both cases is 100%. Now let's see what SRTF does. So C is gonna run, then it's gonna do I/O. And while it's doing I/O, between A and B, they're the same. So A is gonna run. So one of them is gonna be chosen and one of them is gonna run. The moment C is done, so here, let me go back to round robin. Here when C was done, C goes back to the list. So A and B were there. Now C goes to the back of the list, so it takes some time for C to get rescheduled again, depending on which task is running. Now here, the moment C goes back, it gets scheduled right away because C becomes the new shortest task. So C will run, then again A, and this will continue for a week, right? Until A is done, then we go to B. And one thing to note is that the moment A starts, for further decisions, A has to be chosen. We can't switch to B because this is shortest remaining time. So if you execute even one instruction out of A, then the remaining instructions of A will be less than B if we assume A and B are equal. So A becomes shorter and shorter and shorter. So the moment you choose between the two, you keep going with that choice. But then again, every time C is ready, C will be scheduled. And if you do the calculation, you'll see that now I/O utilization is much better. It's about 90%. Okay. So what are the problems with SRTF? Let me see how much time I have. Okay. So let's see what are the problems with SRTF. So the first one is the starvation of large tasks. As you could see in the previous example, B will be starved this time. The other thing is the overhead. So you probably will end up doing a lot of context switching if you, for instance, compare to round robin with a high with a long time quantum, because every time a small task comes, you're gonna preempt and then you're gonna run that. And in some cases, it's unfair. So the fact that you can starve tasks shows that it's unfair. But most importantly, it's impractical because it requires you to know the execution times of your tasks. And that is not something that you always can do. So one way some systems do this is they ask their users to estimate how much time each task is going to take. And they ask them to submit a requirement for their tasks. But then how can you trust your users? Even if you don't have malicious users, it's actually hard for users to know exactly how long their tasks are going to run. Many of tasks are dynamic and so on and so forth. Yeah, this example I like. I should have actually brought up the supermarket example from the beginning. So the supermarket example is like you go to the supermarket, you just buy milk, and that's the only thing that you have. And then you want to check out, you get someone with a full cart in front of you. That would be basically FCFS. So because they came first, they're gonna be served first. So even though you only have one item, you're gonna wait for that customer in front of you. Now, with SGF or with SRTF, you're gonna be served first, the one that has the least amount of work. But then if that's the case, then tasks could or customers could just game the system. They could just put their cart somewhere, take one item at a time, come in, get served, and go back, take another item, take another item. So you can basically game the system. Okay. So there are, if you really want, okay, I got a question. So could we conclude that SRTF is preferred when tasks have higher CPU burst than when tasks have higher I/O bursts? So the answer to this question is SRTF is preferred in all cases if you care about average response time, because it could provably achieve the best average response time without any regards to how much I/O you do. Okay, so if you really want to implement SGF, you could have an adaptive predictor that would dynamically make predictions based on past behavior. So this is one example, for instance. Let's say you have a task that iteratively comes, does some CPU burst, and then goes to do I/O. So you get samples of how long it took for that task to run. So let's say in this case, in this figure that you can see, on the x-axis I have time, and on the y-axis I have time. Let's say the first CPU burst was 6 time units, then 4 time units, then 6, 4, and then it got like a whatever 12 point something. So these are the samples that you're going to get dynamically as you execute your task. Now you can fit a curve to these numbers that you're getting. Hopefully most of you are familiar with machine learning and methods that could be used to make predictions. So usually what we're talking about is a function that gets your previous execution times or CPU bursts and then makes a prediction about your current CPU bursts. So there are different functions that could be used. You could potentially use a neural network here. You definitely don't want to if you're in operating system because you want to make decisions really fast and you don't want to take a lot of time doing matrix multiplications and such. But theoretically, you could. Now there are functions that have been used as estimators. This is one, exponential averaging, which would only look at the previous time that you had. So it would somehow, it looks at your previous one and the previous guess. So this previous guess hopefully incorporate in itself information about all the past ones, and then you look at your previous prediction, you look at what really happened, and then you make a prediction, a new prediction this way. So basically, by changing this alpha, let's say if you make alpha equal to 1, your prediction is basically saying that whatever it took last time, it's going to take this time as well. So very rigid prediction. If you bring alpha to 0, then you're basically ignoring what happened in the previous time, and you're putting all your money on the average that you guessed previously. So by basically changing this alpha, you're putting weight on very close past and your old prediction. So here is a side that we're going to talk about, and we're going to come back to it later on, and that is application types. So when it comes to predicting CPU bursts, what matters in CPU bursts is to identify tasks that would benefit from immediate attention from the scheduler and from the operating system. Let's say that you have a multimedia application running. You have a streaming application that is running. So you really don't want the audio or the video to lag behind. But then these applications also do a lot of I/O. So if you can correctly predict the type of your application, you can give your applications more priority through your scheduling policy to be served immediately when they are ready to be served. So it's actually very important to know the type of your application. That being said, how can you actually predict the type of your application? By just looking at past data. So for instance, if you have applications that have short CPU bursts and then a lot of I/O, you might think that these applications are interactive applications, like it's like Bash, for instance, that you're interacting with your application. It does some I/O, some CPU, it does I/O, and does this iteratively. But what if it's some other application that is showing the same characteristics? So it's actually hard to just look at the past behavior and then predict. And this was a problem actually in one of the, I think, O1 scheduler, for instance, which was used, if I'm not mistaken, before CFS. In Linux, it was trying to identify application types. And based on that identification, it was trying to prioritize interactive jobs like games, like multimedia applications, to get a better response time. But what happened during time was, like, because of those predictions were not accurate enough, some other applications which were not interactive would be identified as interactive and would be served fast. And some applications that were interactive, because they were not being identified as interactive, they would get less CPU time, and then their entire application behavior would change. So at the end of the day, O1, this is one of the main reasons that it got out of Linux's scheduler, because it was basically trying to use hacky methods and heuristics to identify application types, when in general, it's actually very hard to identify application based on their past behavior and characteristics. Okay, so I'm gonna actually stop here. I'm basically out of time. So thank you for those who attended the lecture. Again, the quiz will be released sometime this afternoon or this night, tonight, and you will have time until the Monday after the reading week. So with that, I end this lecture. Hopefully talk to you on Friday. Take care and be safe. Bye-bye.